Okay, you should be able to see me now. And,
Yeah, I can see you.
and I'm not frozen. Good. Okay.
Yeah.
Anyway, so I won't be available for office hours tomorrow. I hope everybody got my email too. So just as a reminder, scope quiz is due tomorrow, so I'm hoping, I'm only talking to one person right now, but I hope whoever watches realizes that it's due tomorrow.
I think Jacob popped in too, but I think both of us took it on Friday.
Yeah, three of you, I think three of you, actually four from our group have already taken it. So I think there's just two more people from our group that have to take it. From my other class, I still got maybe 8 or 10 people who have to take it. Chapter 30 is due on the 12th, and the BioSavar is due tomorrow. And I did find somebody found a mistake in the BioSavar worksheet. I typed something in incorrectly, so I fixed that. I think it was problem 1C. I typed something in incorrectly. So it should be, that part at least should be okay. I apologize. These are all new worksheets that I put on Zoom. It just makes it easier for grading. So the only bad thing is I don't get to see your work. So today what I want to do is really, again, look at the force on a wire magnetic field, but a little bit differently though, because we're going to look at the force on a wire in a magnetic field due to another wire that's producing the magnetic field. So we'll talk about some examples because your homework problems have several examples of this. We're going to talk about Amperes Law, which is another way to calculate the magnetic field, and then we'll start on the next chapter. Probably this will be the second half of the lecture. Okay. And it is the last chapter in the unit is very demonstration intensive, so I have a lot of demos on my desk today. Of course, they're better live, but it's okay. All right. So last time on Friday in lab, we talked about the magnetic field due to a long wire. We actually did it for a short wire using the BioSavar law. So we calculated the magnetic field due to a current carrying wire at some point P above the wire. And then what I said was, let's let the wire get infinitely long, and I was able to get this expression. And so this is the magnetic field due to a long wire. Of course, if you don't have a long wire, if you're real close to it, the wire is going to look long. So you can still use that equation as an approximation to the magnitude of the magnetic field produced by the wire. And of course, the direction of the magnetic field you get by pointing your thumb in the direction of the current and your fingers where curl around in the direction of the magnetic field. And again, use a right-hand rule for that. Okay. We also calculated the magnetic field due to a wire loop with the BioSavar law. And you know, unless I ask you on the exam to derive these, they'll probably be listed on the equation sheet. You might, if you need to use them. Okay. What I want to do is look at the magnetic force between two wires. So I want to look at this particular problem. And I'm not going to, for now, I'm not going to label the wires I1 and I2 because it's easier for me to illustrate what's going on using different colors. So I'm going to draw a red wire. Carrying current I red. I guess we'll call this I1. At the end, we'll call it I1, but I want to refer to it as a red one, just because it's going to be easier to distinguish between them. And here's a blue wire. So both wires are carrying current to the right. I want to know the force on the blue wire. So I want and you really want the magnitude of it. Actually, I want the magnitude and direction, so I'm going to say something a little bit about both. But I wrote this without the arrow over it because I'm interested in calculating the equation for the magnitude. And we'll use the right-hand rule to determine the direction. Okay. Does this blue show up okay?
It's all right for what you have so far, but the F blue is just a little hard to read.
Okay. Let me rewrite it.
No worries. I can see it so far.
Okay, I'll try pressing harder. So I want to find the force on here. The problem for the first problem we got to deal with is the fact that these wires are long, they're infinitely long. So I really can't calculate the total force on the entire length of the wire because the force will be infinite. Because you know the equation for the force on a wire is I L cross B. That's for the case where the magnetic field is uniform. And it turns out that the magnetic field that this wire is experiencing, the blue wire, is going to be uniform along the wire. And the reason why is because of the fact that the field due to the red wire depends on 1 over the distance. Well, the distance between the two wires is constant if they're parallel. Okay. Just 1 second. Okay. Sorry, I missed. I didn't see you there, Jacob. I didn't see that in the chat. Okay. So let me draw the magnetic field due to this top wire. I'm going to use red. If I use the right-hand rule, my fingers curl out of the board at the top, above the wire, but below the wire, they curl into the board. So the blue wire is experiencing a magnetic field into the board. And the value is the same all the way along the length of the wire. So that means that I can treat the magnetic field as uniform in calculating the force on this wire. And the other thing too is the magnetic field is perpendicular to the direction of the current. So if I want to calculate the magnitude of the force on this thing, and again, I don't want to calculate the force. I think I lost my train of thought. I want to calculate the force per unit length. So I'm going to divide the L out. Okay. But before I divide the L out, let's just talk about, since these two are perpendicular to each other, F is I, L, B. I want to calculate the force on the blue wire per unit length. It's just I times B. The I is the I of the blue wire. And the B is the magnetic field due to the red wire. Are we okay so far? So I kind of went in circles a little bit there. Sorry.
I'm good so far.
Okay. All right, so then I have to write the expression for the magnetic field due to the red wire. Which is given by this expression. The R then is basically going to be the distance between the two wires. And I guess we'll call the distance between the two wires D. So that's the magnitude of the force per unit length on the blue wire. We can rearrange it.
Hey, Professor, I have a quick question.
Yeah.
I might have missed this from one of the previous lectures, but that mu naught, what is that symbolizing?
It's the permeability of free space. So mu
Oh,
naught.
okay.
So yeah, it's the 4 pi times 10 to the minus 7 Tesla meter per amp, and it's the magnetic analog of epsilon naught.
Okay, thank you.
Okay. So this is this expression for the force per unit length on this wire. Now, what is the direction of the force? Let me draw a coordinate system. The magnetic field is into the board. The current is to the right. So use the right-hand rule. Point your fingers in the direction of B, curl them in the direction of I, curl them towards B. The force is upward. So F blue per unit length is upward. And it's given by this value. Now, what do you expect the force on the red one to be due to the blue one?
The same thing, just downward?
Yeah, it's the same thing but downward. Newton's third law. So in general, the force between two wires can be written, if I call the currents I1 and I2, and let me just rephrase that. The force per unit length is mu naught I1, I2 over 2 pi, and the R is the distance between the two wires. Now, if these wires were not infinitely long, but they were close together, in other words, if this length was much greater than R, then I can calculate the actual force on the wire, right? I can approximate the force on the wire by multiplying both sides by L. Isn't that true? You know, if my wires were like this, and this equation is valid even though these are infinitely long, because this is a pretty valid expression for the magnetic field due to one of the wires. So I can still calculate force on one of these lengths of wires when these two are real close together, because when they're real close together, the wires do look very long. Okay, I want to show you that the force on the red one is downward. Well, and it should be obvious to you that, yeah, the magnitude is going to be the same thing. But let me just for more practice with the right-hand rule, I want to draw the magnetic field here as a result of the blue wire. If I use the right-hand rule, the magnetic field due to the blue wire is out of the board. Above the wire. And below the wire is into the board. So if I want to find the force on the red one, the red one has a current to the right, but then the magnetic field is out of the board. You point your fingers in the direction of the current in the red wire, and then curl them towards the magnetic field. Well, I can't curl my fingers this way, so I got to flip my palm over and then curl them this way. So my thumb points downward. So the force on this wire is downward. So that means that the two wires attract. So when the currents are in the same direction in both wires, they actually attract. And the magnitude of the attraction, the force of attraction per unit length, is given by this expression. What if I flipped? What if I flipped one of the currents around?
Would one repel and one attract?
Well, you really can't have one repel and one attract. Right? I mean, because you have to obey Newton's third law. So if I flip this over in the opposite direction, this would want to move downward. You're right. But then according to Newton's third law, this has to move upward. Right?
I see it now. Thank you.
Yeah. So they would repel each other. Okay, so the currents in opposite direction repel, currents in the same direction attract, which is goes against what you learn about forces on wires, right? I mean, not forces on wires, forces on charges. Because when dealing with forces on charges, like charges repel, unlike charges attract. Here, currents in the same direction attract, currents in the opposite direction repel. So sometimes that's confusing to students. By the way, if you get a set of wires and you separate them by a meter and you run 1 amp through both wires, then the force per unit length is given by the following. This ends up being 2 times 10 to the minus 7 newtons per meter. This you can measure, and so you can do a mechanical experiment. You can adjust the currents until the force between these two wires is this value. And you can measure this. You can do this with weights, like milligram weights. Okay? So you can adjust the current until the force between the wires is given by this value. And we can use this then to define the amp. When we're in person, I do a lab with 2 wires, 2 finite size wires. And these are, one of them is fixed, the other one can move up and down. And what we do in that lab is we measure this quantity mu naught. We use a laser too, so you can see how how these separate when you increase the current. And we use masses, so we balance the force between the 2 wires due to the magnetic field with the force due to gravity, and use milligram weights. So this is actually not super hard to measure. And so as a result, we can use this idea to define the amp. And this is discussed in your textbook. Okay. Let's talk about a couple of things regarding wires, because forces on wires, forces between current carrying wires. Now that we know that expression, and that we know that currents in the same direction attract, currents in the opposite direction repel, we can do a whole class of problems. So imagine you have, and I'm not going to solve this problem, I'm just going to talk about how to approach it. let's say we have 3 wires. The wires come out of the board, okay? Or the wires go in and out of the board, but the currents, I'm going to tell you which way the currents are. Let's pretend that these are 3 wires in an equilateral triangle configuration. These 2 currents are out of the board. This current is into the board. And my job is to calculate the force on that top wire. Okay, remember, this is an equilateral triangle configuration. What is the first thing that I do?
Find the magnetic field due to each wire?
Yeah, you mean these 2?
Yeah, I mean, I was thinking all of them just for sake, but yeah, if we're trying to find the force on the top one, then yeah, just the bottom 2.
Because I'm interested in this one, right? I'm just interested in the effect on this one. Only these 2 are going to affect this one. So, granted, the field produced by this one is going to affect the other 2, and I'm not interested in that. But you're right. I can calculate the force, the magnetic field to these 2. But I want to do something else first. Anytime we do a force problem, what's the first thing that should come to your mind? What picture do you draw?
Force body diagram.
Okay, so anytime you have a force problem, the first thing that's got to come to your mind is, I got to draw a free body diagram. Okay? It doesn't matter whether it's in 205, 210, or 215. Okay? That's actually at any level. If you have a force problem and you're applying Newton's laws, then you want to draw a free body diagram. Of course, and I got to be careful what I said at any level, but when you take a junior level class, you learn a different technique to solve problems. But if you're told to apply Newton's laws, you got to draw a free body diagram first. Okay, so what can you say about the force on this wire due to the bottom one? They carry currents in opposite direction.
They'll repel each other?
They'll repel, right? And they're going to repel along the line joining them. So there's one force. We can call this F1. I'm not going to be, I should be more careful about calling these forces. In fact, I should call this 1, 2, and 3. But if I do that, this is the force on 1 due to 3. But I'm not going to solve the problem. What about these 2? What's going to happen to this top wire as a result of wire 2?
Same thing, they'll repel each other.
They'll repel along the line joining them. Okay. Now, yeah, I could do what you said, calculate the magnetic field at this point due to this wire, and the magnetic field at this point due to this wire. However, I already know this expression, right?
Yeah.
So I just need to calculate the magnitude of this force between these 2 wires. And I got to be careful, the force per unit length, right? Because these are infinitely long. And I got to calculate the magnitude of the force per unit length between these 2 wires. And in fact, if these currents are the same, let's all make them 1 amp. Then the magnitude of 2 forces are the same. And since this is an equilateral triangle, can you tell me what is the direction of the net force?
Directly upward?
Directly upward, because the x components cancel. The y components are both up. but the x components are in opposite directions. So this is a problem like the Coulomb's law problem you did with charges. It's the same kind of problem. The only difference is in calculating the magnitude of the force between these two, you have to use this equation. But you still got to draw the free body diagram. Once you know the magnitude, then you got to break it up and the force into two components, one in the x direction, one in the y direction. Okay? Does that make sense?
Yeah.
Okay. I want to discuss one more thing, because this you'll see problems like this in your homework, and you'll see different geometries. I want to talk about magnetic fields. Let's say we have a long wire. We know that the magnetic field due to a long wire is given by this expression. So let's say we have a long wire with a current out of the board. And I want to calculate the magnetic field at this point, P. Obviously, the magnitude of the magnetic field due to this wire is given by this expression. Okay? So the magnitude is given by that expression, whatever this R is. But what about the direction? What is the direction of the field at that point?
The direction of the magnetic field?
Yeah, what is the direction of the magnetic field at point P?
Upwards?
You're right, it's upwards. You use the right-hand rule. So I'm going to draw a circle around this point. That's supposed to be a circle, okay? And you know that the magnetic field circulates in the following direction, true? Okay, you're pointing your thumb out. And you know that the magnetic field at any point in space is tangent to this field line. So I draw a circle of radius, whatever this distance is, and then I draw a tangent line at this point that's supposed to be upward. Like so. What if I asked you the magnetic field at this point? Well, then I would draw a tangent line like this. This line is tangent to the radius of the circle I drew. Sorry, let me redraw that. That's supposed to be a straight line. If I know the coordinates of this point, and I know this angle theta, then I can get this angle alpha. That'll give me the direction of the magnetic field. And then the magnitude obviously is just going to be given by this expression. So if I want to find the magnetic field direction due to a long wire, really what I want to do is locate my point P, draw the field line, which for a wire is a circle. And then I draw a tangent line to that point, and then I do some geometry to figure out the actual direction. Does that make sense? So like if I do this one here, I'm going to draw a coordinate system. This is 90 minus theta. This is theta. And this is 90 minus theta. So alpha is 90 minus theta. So this the direction of this field at this point is 90 minus theta. So as long as you know the coordinates of this point, you can figure out this angle, and then you can figure out the direction of the field. Are we okay with that?
Yeah, I'm good with it.
Okay. Let's do another example. This time we're going to do the force on a wire in a non-uniform field. So let's say I have one long wire carrying current I1 and a loop of wire carrying current I2. And the distance, the closest wire is from I1 is D. And the furthest distance D plus A. And this length is L. I want to calculate the force on this loop of wire. Now we learned a couple days ago, or a week ago, I'm sorry, that the force on a wire in a uniform magnetic field, I'm sorry, let me rephrase that. The force on a loop of wire in a uniform magnetic field is 0. But in this particular case, I1 produces a non-uniform field because as you get further and further away from the source of the field gets smaller. So the field here is greater than the field here. So the force on this wire is going to be less than the force on the top wire in that loop. Okay. Now, what helps us in doing this calculation is that along any wire here that's horizontal, the field has the same value. So even though the field on the top wire is different from the field on the bottom wire, along any wire, the field has the same value, at least the horizontal ones. We'll talk about the vertical ones in a second. So I can still use and it's going to lead me to this equation. And since L is not infinite, I can actually calculate F equals U naught I1 I2 times L over 2 pi r. So I can actually calculate the force because these wires are not infinitely long. So I can calculate the force on this guy due to the top wire, and then the force on this bottom one due to the top wire. But what about the ones on the side? They cause a problem because along this vertical wire, the magnetic field does change. See, on the horizontal wire, the magnetic field does not change. On the vertical wire, it does. So what do? I want to find the total force on the loop.
Won't the forces on each side of that cancel each other out? Because even though they're gradually changing as you get farther away, they're opposite directions of the current they're carrying.
You're absolutely right.
Okay.
So I don't have to do those calculations. Isn't that nice? It saves me a lot of trouble. So all I need to do, if I label my sides 1, 2, 3, and 4, I got to calculate the force on 2 plus the force on 4. Of course, the forces are going to be in the y direction because these two are going to attract and these two are going to repel. So this force, the force on this top one is going to be upward. The force on the bottom one is going to be downward. So I wrote this as a vector, but now I'm going to write it in terms of components. I'm just going to write F2 plus a negative F4. And these are all in the y direction. And so F2 is going to be mu naught I1 I2 L over 2 pi d. And then the other one, the force on this one, is going to be downward. And so that's my total force. And I can factor out some terms. That's it. So that's my total force. This is a common geometry you'll see in in textbooks. You'll see it again in the next chapter too, for a different reason. What can you say about the torque on this loop? Due to the wire, what's the torque?
Zero, I
What?
think.
Yeah, why is it 0?
Because the force. Gosh, I can't. I don't know. It's like I understand it intuitively, but I can't explain it mathematically. But they're like in the same direction or parallel.
These two are in the same direction.
Yeah.
The vector representing mu points perpendicular to the plane, right?
Yes.
The magnetic field points perpendicular to the plane. So these two are parallel or anti-parallel, so that torque is 0. Because the torque wants to rotate mu in the direction of the magnetic field. It's already in the direction of the magnetic field. So the torque is 0. You can do it in terms of forces. It's a little bit harder probably.
This mu that we have here on the board for the torque, that's the one that's I times a vector, and our a vector is that one that's the normal to the loop, right?
Yeah, so it'd be into the board.
Cool,
Right,
thank you.
I use my right hand rule, I curl my fingers in the direction of the current, my thumb points in the direction of the board.
Mm-hmm.
And so yeah, so it points into the board. The magnetic field points into the board also. And so they are parallel, so yeah, the torque is 0. And even if they were anti-parallel, the torque was 0. Okay. What if, okay, I'm going to ask another. I'm asking a lot of what if problems. I'm just trying to look at the system as many different ways as I can. I guess the more information we can get out of this system, the better we understand the physics. What if I wanted to calculate the force on just side 1? Well, then I have to break this up into a bunch of DS's. And my DS is in the y direction. And I know the cross product of this with the magnetic field will be upward. All right, I'm going to use dF is I ds cross B. And then I'm going to integrate over the wire. And granted, these are perpendicular to each other.
Hey, Professor.
Yeah.
That ds you have on the board, that's a dy, like an infinitesimal dy,
Yeah, it's
right? Okay.
Yeah, so I'm calculating the force on a small piece of wire because if I make it small enough, the magnetic field over that little piece of wire is going to be the same, has the same value.
Yeah.
Okay, so I got to break it up into a bunch of teeny tiny pieces, figure out the force on each one of those teeny tiny pieces, and then add them up, which means you have to integrate.
Okay, cool. Thank you.
And so this is I2. I got to be careful now. And this is B due to wire 1. And so this is going to be I2. And I'm doing it kind of intuitively. I'm not being very systematic. I know the force is going to be upward. My ds is in the y direction. And B, then I got to write B because this distance is y from the wire. I got to write in terms of y. And then F, I just got to integrate from D to D plus A. And yeah, I'm not being super careful about, all the plus and minus signs. I'm just using intuition, knowing that the force will be, each one of these are going to contribute in the same direction. I'm calculating the magnitude of this force, and this is going to be logarithmic. I forgot the L. Oh no, there's no L, sorry. So this is the magnitude of the force.
And which direction did you say the force was again?
Well, okay, so if you want to be, so let's do, yeah, I said upward, that's a mistake.
No worries, I was just double checking that it was outward from the loop.
Yeah, it's going to be in the x direction. It can't be upward. So let's do this then. This current's in the j direction. The magnetic field's into the board. This is in the minus I hat direction. So it's actually that way.
Okay, cool. Thank you.
Okay. Yeah, I was focusing on the magnitude, but it's important. You're right. It's important. I should tell you the direction of the force. It's in the minus I hat direction. Okay. So I've kind of exploited this problem as much as I can. So the next thing now we're going to talk about another way of calculating magnetic fields. Suppose I have a long current carrying wire. And we know that the magnetic field forms circles. That's not a good picture. The slide has a better picture. Okay, the magnetic field forms circles like so. Suppose I integrated around a loop of these field lines. In other words, let's let this radius be r, this distance be r. Let's integrate around that field line. I want to take the integral around a closed loop can I do that? Well, the magnetic field has the same value around this loop. It's given by this expression. R is constant. The magnetic field and the direction I'm integrating are the same. So this is going to be integral of whatever B is times my arc length and then it's going to integrate over the whole circle. And the magnetic field due to a wire this integral, sorry, the marker's too light. This integral gives me mu naught times I. So in general, the integral of B dot dl is equal to mu naught times I. And I is whatever is enclosed inside the loop. So this is true in general. You need the principles of vector calculus to prove it in general. I'm not going to do that. Okay? So I did it for a simple case, but it's true in general, where if you integrate the magnetic field around a loop, it's always going to be equal to mu naught times I, where I is whatever current's enclosed. This is called Amperes Law.
Here, the current that's enclosed is just the current through the wire, correct?
Yes.
Okay.
Yeah, the current in the wire. So this wire penetrates the surface in fact, this wire penetrates any surface enclosed by the loop. Isn't that true?
I'm sorry, I'm a little confused by your question.
So this wire penetrates any surface enclosed by the loop.
Oh, yes, correct.
Right? In fact, this is true for any surface enclosed by the loop. And one can see that if you apply the rules for vector calculus. Okay. Now that surface that is, this is an open surface. And as a result, you can enclose a lot of surfaces with this loop. And so why then should the loop care about which surface it encloses? And like I said, the fact that it penetrates this loop, it means that it penetrates any surface enclosed by the loop. So this has to be true for any surface enclosed by the loop. And I'm saying this and I'm making a point about this because I'm going to have you watch a video later where we have a problem with this principle. We have a problem with this law. Okay? For now, this is correct. But if I varies with time, then this is not true. It won't be true for any surface enclosed by the loop. And so we have to come up with a correction factor. So I have a video, instead of doing it in a lecture, I have a video I created where I want you to watch. And it'll be probably, I'll have you watch it over the, probably have you watch it over the weekend. You have to watch it after I do my lecture today. Okay? And we have to come up with another term here. It's going to be called the displacement current. Now, What if the current, if we have two currents going in opposite directions? Two equal currents going in opposite direction. What's how much current is enclosed? All right, if this is 1 amp and this is 1 amp, they go in opposite direction, then this integral is 0.
And if they're going in the same direction, it's 2 mu naught I?
Yeah. Well, it's just 2 times, if it's, 2 mu naught I, yeah.
Okay.
They add. Okay. And be careful with, the direction of these integrations, right? B is going to be, the direction of B, if the current determines the direction of B, right? If you integrate in the opposite direction, then you're going to get a minus sign in here. So this is analogous to Gauss's law because we can use this to calculate magnetic fields. Because you remember Gauss's law was this. Here this I is I enclosed. This is the I enclosed by the loop. This is the Q enclosed by a surface. And then if my geometry is right, I can solve for E. Well, here, if my geometry is right, I can solve for B, except that my restrictions are much greater here. So then there's less problems I can do where I can solve for B. In order for me to be able to solve for B, I have to be able to pull the B out of the integral and then solve for it. And the symmetry restrictions are higher for Amperes' law than they are for Gauss's law. So there's less problems I can assign to you. And so the problems I'm going to do today are pretty much all of the ones that you can do. There's really one other one. And it is in your book. I think it's one of the red coded problems in your book. So the geometries I'll do today are pretty much all the geometries except one, I think, that we can do. So the difference here between the two is here I just have to integrate around a closed loop, not a surface. And the current I is any continuous current passing through any surface bounded by the closed path. And again, we need a high degree of symmetry to be able to apply Amperes' law to solve for B. Amperes' law is always valid. It's just that if I want to use it to calculate B, I need a high degree of symmetry. Also, I need to have B to have the same value around the loop I choose, whatever loop I choose. This integral is a measure of what's called the circulation of a vector, or the curl of a vector. Okay? This measures the ability of it tells us that the field has a tendency to rotate, or it tends to rotate objects. Is this a vector that causes rotation? Okay? This tells us that this is a vector that produces rotation if this is not 0. If it is 0, then it does. If this integral is 0, it doesn't produce any rotations. So when we did this integral for the electric field, this tells the electric field doesn't produce rotations. The electric field doesn't circulate. The electric field doesn't curl. Okay, the magnetic field does. The magnetic field forms closed loops. In fact, there's a relationship involving a vector calculus thing called a curl in the magnetic field. And it's non-zero.
Hey, Professor.
Yes.
Kind of an off question, but in a real life wire, does this cause like the outside part of the wire to twist more?
Because the magnetic field curls?
Yes.
So you're asking, does the field
Oh, wait, no.
Produce a
Because that's
force on
not the
itself.
force.
Yeah.
Okay, yeah. Thank you.
Okay. So let's do a couple of examples. I think these examples will carry us to the end of the first half of the lecture. So now we have Amperes Law. And for some reason, it's common to use dl instead of ds. Oh. So let's say we have a thick wire with a uniform charge density. In your homework, there's one of these problems with a non-uniform charge density. Okay. So this is a thick wire. The radius of the wire is r. And let me draw a cross section of this thing. So that you have current. Let's say the current's going to the right, and let's make the current come out of the board. I want to calculate the magnetic field inside and outside the wire. I'm going to assume that the wire is made up of a material whose permeability is mu naught. Okay? That's not a real system, but let's pretend that the material it's made out of is mu naught. I can choose a material in which mu naught is some constant times it, but let's not worry about that for here. And your book does that too. Okay. Let's calculate the field inside. I want to use this. I know that the magnetic field is going to form circles inside and outside the material. It's a long wire. Magnetic field is going to look like this. Inside. And since the density is uniform, the magnetic field anywhere along here is going to have the same value. So I'm going to choose a circular path that matches this field line. It has a radius, little r. And so, but for me, setting up this integral is going to be easy because my b is going to be parallel to my dl. B is going to be the same all the way around. So this integral is just going to give me b times the circumference of the circle. And this is going to be equal to mu naught times I enclosed.
So your DL is an infinitesimal piece of the arc length.
Yeah, it's
yeah.
RD phi.
Okay.
I mean, I skipped that step, right? But
no worries. I still see what you're saying.
Okay. So now the hard part, now I got to figure out how much current is enclosed inside this wire, inside this area. If you remember, current is current density times area. But if the current density is not uniform, then dI is J dA. Actually, it's J dot n hat dA. But most of the problems we're going to be doing, these two are parallel, so a lot of times I ignore it. It's unusual for us to do a problem where these two are not parallel. Okay? Then, the normal to the cross-sectional area of the wire. So how do I figure out I enclosed? Well, if my DI is JDA, and we're talking about this circle, remember how we broke up circles earlier? Earlier, this semester, we would say dA is 2 pi r dr. We break up this disk into rings, because you got to integrate the current density of an area. My J is easy to calculate because the current density has the same value everywhere in the wire. So my current density is just my total current divided by the area, the cross-sectional area of my wire. So if this R is half the radius, then this purple circle is going to enclose a quarter of the total current in the wire. So what does this come out to be? So I get B times 2 pi r equals mu naught times the integral from 0 to r and again, I have too many r's here. I'm going to make these r primes. And what do I get when I integrate this? And so I can solve for B. And so the magnetic field inside varies linearly with R. If the current density was linearly dependent on R, then the magnetic field would depend on R squared. So it's going to be 1 power higher than the density. Now, what about outside? What about out here? Well, then, if I'm out here, then I got to choose a bigger circle. But if I choose a bigger circle, then this I enclosed is just the total current I have, right? And so for little r bigger than R, I just get the field due to a current carrying a wire. And when you let little r be big R, you get that these two terms are the same. Now, if you graph this, inside it's linear. This linearly depends on R. And then outside it decreases as 1 over R. Looks like that. In the homework, you have one with a non-current charge density, and so the charge density becomes part of the integration. You actually have to go through and do the integration. You can't really pull anything out of the integral. Okay, so you have one in the homework where your setup is just like this, except that J is non-uniform. Okay? So let's do another geometry. And usually our textbook and several textbooks do this problem very quickly. We're going to do this next problem with a little bit more thought. Because I want to show you how you can use Amperes Law, basically. The next problem I want to do involves something called a solenoid. A solenoid is just a coil. This is a solenoid. Okay? And it will produce a magnetic field. One of the demos I haven't done yet. I gotta make sure this is plugged in. Hold on a second. Is that a current carrying wire produces a magnetic field? So I kind of want to demonstrate that for you right now. I gotta plug in my power supply. So I have my coil and I have a compass. Okay? And so what I want to do, and this happens quick, I can't have the power turned on very long because I'm gonna blow a fuse. So I'm gonna turn it on real quick and you should see the compass rotate. Did you see that? So that tells you that the wire produces a magnetic field when it carries current. And this is a coil of wires, call them solenoid. Do it one more time. Okay. You can see the compass aligns itself with the magnetic field of the solenoid. And solenoids have a lot of applications in real life. Like for electromagnetic valves. I don't know if you've heard the term solenoid valve. You would see them, let's say, solenoid, you'll see them in a car, doorbells. Sprinkler system, the valve on your sprinkler system. If you have an electronic sprinkler system that turns on at a certain time. Okay. So there's a lot of applications of solenoids in real life. And what you do is a lot of times you put a bar magnet inside the coil. So you put a bar magnet inside the coil. And imagine once the current goes through it, not a bar magnet, I'm sorry, a piece of iron. Once the current goes through it, the iron gets magnetized, and the magnet, if it's near something that's magnetic, will be attracted to the other magnet, and that could cause maybe a current to flow. So it'll act like an electronic switch. Okay. So I want to determine the field to a solenoid. Now, the general problem for calculating the field due to a solenoid is actually not easy. If you calculate the field due to 1,000 loops, that's a lot of work. In your notes, I do the field due to one loop at the center of the loop out of the plane of the loop. So the rest of your notes that you have, I've done examples for you to look at, and I've solved them in complete detail. So I did a loop out of the plane of the loop, but then I did the solenoid by taking that loop, the field of that loop, and integrating it over a bunch of them. But I want to calculate the magnetic field using Amperes Law. So if you draw a solenoid, and we're going to assume that the solenoid, its length, is much, much greater than its radius. So we have a bunch of wires wrapped around a tube. And these are tightly packed. And the way I've set it up is the current goes like this. And if I use the right-hand rule, you can kind of see that the magnetic field kind of looks like this. In fact, along the axis, it's horizontal. Off axis, it's a little bit off horizontal. If I make this long and narrow, essentially all the field lines will be pretty much horizontal. I want L to be much, much greater than R. And what that'll do is make the field inside, even off axis, pretty much horizontal. Because if you don't have a long a long solenoid, if you have a short one like this, where the length is not that much greater than the radius, then the field due to this, when you run a current through it, is going to behave like that of a bar magnet. And so the idea then is you have a bunch of field lines pointing horizontally, even the ones off axis, when you let L much, much greater than R. And then the field lines will wrap around like this to the other side. And these field lines that come around the other side are essentially going to be horizontal. If I'm in the middle of this really long thing, they'll probably be horizontal. But if this is infinitely long, wherever I go, it's going to look the same. So we're making the assumption this is really long compared to R. In fact, infinitely long. And so if we make it infinitely long, then whatever field lines come out, they have to be horizontal. And so I want to use Amperes Law to calculate the field out here and the field in here. All right, so I'm going to draw an Amperian loop. And I can do this above and below my solenoid. Since I don't have any space up here, I'm going to go below it. The slide that you see, I draw my Amperian loop above it. I'm going to integrate in the following manner. I want to calculate the integral of B dot dl around the loop. And we said that outside the solenoid, the field is essentially horizontal. So to a good approximation, the field is horizontal. That means that B dot dl here is 0. And that B dot dl here is 0 because the magnetic field is perpendicular to the path. But this is not necessarily 0. But they are equal and opposite. Why must these terms be equal but opposite? Because there is no current enclosed inside this loop. So these terms, when you integrate over them, have to produce two contributions that are equal and opposite. Because there's no current enclosed in here. So that says that B outside the solenoid is, the least I can say right now is that B is uniform. But in reality, B is 0 outside. Well, how can I say that? And how can I prove that? How can I prove that B is 0 outside? Well, there's no current going through here. How big is my Amperes loop? How big can I make it? I mean, I can make it as big as I want, right? What if I make these lengths infinitely long? If this is infinitely far away, what's the field? If I make this part infinitely far away, what's going to be the field over that wire?
0?
0. Well, if the field is 0 over this wire, then the field has to be 0 over this wire, isn't it true?
Yeah.
And then using the same argument above, I can prove the same thing. So the field above and below is 0. Now, the books, they just say the field is 0 above and below, but we can't use Amperes' law to deduce that. You know, we can start with the fact that, yeah, the fields will wrap around like this, but we can prove that it's 0 using Amperes' law because, 1, there's no current going through this thing, and 2 is if I make my Amperian loop go way down to infinity, then this term will be 0, which means that this term also has to be 0. Does that make sense?
Yeah.
And then I can do another Amperian loop inside here. How much current is in there? How much current is in that loop? How many wires penetrate this? In other words, if I take one of these and I draw a square, I draw a square, let's say, perpendicular to this plane inside. There's no current that goes through that loop. There's no current, there's no wire that penetrates this thing. So even for this,
So that square there is like inside of the cylinder, correct?
it's inside, yeah. So there's
Okay.
no current going through there. And I know that if the field is horizontal, these two guys don't contribute. But these two guys do contribute. They have to be equal but opposite. That tells me the field has to be uniform. The field can either, if this is 0, that means the field is either inside is 0 or uniform. Okay. So we can use another loop in here to establish the fact that the field inside here is uniform. Okay, so far so good. So we know the field is uniform here, 0 out here, and out here. I'm going to choose one other loop. And the third loop looks like this. This is going to give me the answer that I want. Because we know the B field is horizontal inside. There's no magnetic field. In fact, the dot product between the magnetic field and this wire is 0. The dot product between the magnetic field and this wire is 0. And there is no magnetic field outside. The only contribution is due to this. Okay, so this is L. And that's going to be equal to how much current is enclosed in this loop. Well, this current penetrates the loop, this current penetrates the loop, and this current penetrates the loop. In fact, if n turns will penetrate the loop, I got to count each one of them. So little n is the number of turns per unit length. So this is the field due to a solenoid, as long as L is much, much greater than R. In your notes, I do a problem. In your notes, I do a problem for the solenoid. So let me get to that slide. Just give me a second. I messed up, sorry. Okay, so I did the solenoid in your notes. First did one loop, and then I just did a bunch of them. So what I want to do is show you the graph of the magnetic field along the axis. As a function of the ratio of L over R. Notice that as L over R gets bigger, how uniform the field is inside the solenoid. Even at L over R equals 50, so if you have a solenoid that's 50 centimeters long and a diameter of 1 centimeter, you get a pretty uniform field. I mean, L over R equal 10 is not that bad either. And so when L over R is big, you can just use mu naught times the number of times per unit length times the current to get you the magnetic field due to the solenoid. So I have these in your notes. You might want to go over it. I also have this problem out of the plane of the board completely solved. So you might want to take a look at that. Okay. Let's check the time. I think that we're a little bit over. Let's take a break here, and I'm going to do one more problem after the break, and then I'm going to start on Faraday's law. And I'm going to spend some time going through Faraday's law. It's probably we'll be able to cover most of the stuff on Faraday's law today, and then next time will be just applications. So let's meet back here about 12:50. Okay?
That sounds good.
Okay. I'm going to pause the recording.